Hello and welcome to Android Developers Backstage. I'm Chet Haas on the Toolkit team.
I'm Romain on the Toolkit team.
I'm Ken Russell on the WebGPU and WebGL team.
And I'm Corentin on the WebGPU team.
Okay, so we have two WebGPUs and one GL. So we should talk a little bit about GL, but probably more about WebGPU. This one is all about WebGPU, but I do want to find out the history of this thing, which relates to WebGL. So why don't we start with what's WebGPU?
Corentin.
All right. So WebGPU is what we say is it's a successor to WebGL. So it's a web JavaScript API that exposes the GPU to JavaScript, so you can do like computations, rendering, whatever on the web. And that's a capability that's already provided by WebGL. So the difference here is that WebGPU is not a native API that was ported onto the web like WebGL was, but instead it's kind of a brand new thing that takes inspiration from a lot of modern APIs so that it works on all of the modern APIs, whereas GL has a lot of impedance mismatch, and also it's harder to bring new features to WebGL. So maybe we should talk about WebGL, Ken?
We certainly could. Briefly, WebGL had a good history and good run, and it's going to be supported forever. Developers can always target it. We're still working on simplifying and modernizing the implementation, but we are certainly beginning to steer developers more toward WebGPU, which we think is definitely the path forward for graphics on the web, compute on the web, and it's a simpler, more portable API.
So I've used WebGL and WebGL2 because there are two WebGLs, and they're close to OpenGL ES, which is the mobile version of GL, but they're not exactly OpenGL ES. But so WebGPU, what is the benefit for developers? I mean, Corentin, you said there's a better match with modern APIs, so I think that's probably powerful for people who implement WebGPUs for the browser vendors. But for the developers, what's the benefit compared to WebGL?
So WebGPU brings features that have been missing from the web. So Compute Shader is the major feature in the first version of WebGPU, and it means that you can get that on all the systems that WebGPU support, whereas it would be harder on WebGL. Also, you see a lot of additional improvements, like, for example, ray tracing in all of the APIs appeared recently, and so it's not in any kind of GL family, and we wouldn't be able to support that probably on WebGL. So not to say that ray tracing is coming to WebGPU soon, but it opens a path to getting a lot of new features on the web.
So I'm curious, this is probably going a little deep a little soon, but how do you see the APIs advancing? Because some of the things that you mentioned are clearly one of the problems that we have with APIs in general, which is, hey, we have the standard that everybody agreed on, and then 5 years later, a new technology comes out that the standard doesn't handle. And then you have to figure out how to shoehorn it in, or maybe you have to come to agreements with some standards committee, or maybe that thing is baked and you simply can't. So what's the plan for WebGPU or follow-ons to introduce new things as they come online?
So for WebGPU, the web API, that's the standard made at W3C, the idea is that when there's technology that coalesces in native, like for example, Compute Shader coalesced 10 years ago or more, then we can bring it to the web because we know things are fairly stable and not going to change very much. Things like ray tracing are starting to coalesce, so maybe we're going to be able to take them in. The fact that WebGPU is not based on any one specific native API means it's a bit easier to keep it going after said API stop development. For example, it's hard to add new features to OpenGL, to WebGL that are not in OpenGL because they're just not there. Whereas WebGPU being decorrelated from that makes it possible to add these features.
Let me underscore that a bit. We considered adding some more advanced features to WebGL, like pipeline state objects and even ray tracing. And while technically possible, we would have had to specify the entire semantics of that and the interactions with the entire rest of the OpenGL ES API. This would have been an enormous amount of work. And we decided in the end it was simpler to just make a clean break and move away from the stateful APIs to one that is stateless, like WebGPU and the native APIs.
Yeah, and I think you put your finger on it. Like for developers, we were just joking about that before the recording started. But GL being this very stateful API, it's extremely easy to make mistakes. It makes also code sharing incredibly difficult because you rely on hidden global variables all over the place. And at least in my experience, most of the bugs I've dealt with in OpenGL, when it was not shaders, it was just some piece of state somewhere that I didn't know was affecting what I was doing. Anyway, and so we're kind of rid of that with WebGPU. But Corentin, you mentioned, so there are modern APIs. We have Vulcan, DirectX 12, there's Metal. How does WebGPU compare in terms of those APIs? For instance, Vulcan is pretty low level. Metal is higher level. Like where does WebGPU slot in those families of APIs?
So there's two axes to the question. There's the axis about performance, and obviously because WebGPU builds on top of these APIs, the performance is going to be at most as good as the underlying API. But we hope to get really close.
Sorry, I slightly disagree here because I know from experience, at least Vulcan, it's easy to misuse it, and so a well-built WebGPU implementation could probably be better at using Vulcan than I am.
So that's the hope, yes. WebGPU in terms of complexity sits, it's barely more complex than Metal. And it's definitely way, way easier to use than D3, D12 or Vulcan. So for example, I think if you want to get the triangle on the screen in native with Vulcan, you probably are looking at like 2,000 lines of code if you want to do it properly and portably. In WebGPU, we just made a demo that's portable also on the web with Mscripten, and it's 150 lines of code, including like window initialization and stuff. So it's fairly small and easy to use. I mean, lines of code are not everything, but there's really a lot of care put in the ergonomics of the API everywhere, like the state sharing, the defaults, etc.
So I assume there are things, because for instance, one of the things that makes Vulcan so, let's say, verbose is that you do have full control over everything. So memory allocation, memory management, you have to do it yourself. I assume that's the kind of stuff that WebGPU takes care of for you because the target is JavaScript, right? Like I don't have to create my own allocators and that kind of stuff.
Yeah, so like you got the finger right on the point for this, which is WebGPU is targeting JavaScript, so we need to do a lot of things for the developer because we don't have we have a garbage collector, we don't have RIAA, or we don't want people to manually free resources. So all memory allocation we do for the user, and that includes also descriptor state allocation, not just buffer and images and stuff. The other constraint WebGPU has is it needs to be secure for the web environment. And in Vulcan, there's a ton of things where if you don't get it right, then you might do something bad with your GPU and you might see someone else's data or whatever. So WebGPU also takes care of all these foot guns, we call them, like memory barriers, uploading things correctly. There's just like a lot of them. So we take care of all of that. So it's easier to use, but also you have less low-level control.
Can I ask a question that'll probably show how ignorant I am of all this stuff, which is how does it actually get to the GPU? So you're in JavaScript, you're writing in web page stuff. Somehow that has to go through Chrome or whatever browser you happen to be running in. Does that mean that all of the browsers implement APIs that WebGPU can then use? I mean, it must have been the same problem for WebGL, right?
To talk about WebGL, Chrome started its life with a remote GPU process, which was, wisdom of the Chrome architects from really the very beginning. It was a stroke of genius. And now all browsers have a separate GPU process for security reasons. You don't have the graphics driver in the JavaScript process anymore. It's a really large, security risk. So there's always been a remoting implementation of the OpenGLES API in Chrome. It ships the commands over to the GPU process. They're validated over there, and then they're executed if they were legal. WebGPU follows a similar pattern, and you're exactly right that there does need to be some underlying API. Maybe Corentin can talk about that.
For WebGPU, we have the hindsight of years of WebGL. So we directly started with both an implementation of a WebGPU C API on top of underlying drivers. We call that Dawn native, in Dawn being the overall library name in Chrome. And there's a second library in Chrome called Dawn Wire, which is the same API, but implemented through a client-server protocol. And that, so if you look at the JavaScript WebGPU calls, the steps it goes through are, it goes into Blink, which is the web API engine for Chrome. Blink calls into the Dawnwire client to serialize the commands. On the other side, the commands are deserialized and call into Dawn native, which validates everything for security and also to make sure your application is correct. And then goes on and talks to what we call a backend, which is an implementation of WebGPU on top of one of the target APIs. So there's a lot of steps. But like, since we knew from WebGL, we knew already what kind of architecture worked, and we went right away with this.
And then presumably all of this is asynchronous because you've got a lot of steps in there, right? So you just send the things over, which we tend to do in, GPUs without all of the remoting processes as well. But like, you're just sending the things over there, and you really don't want to flush things and read the results because that's going to be a while.
So yes, but we go one step further. So normally on GPUs, you don't want to send commands and wait for them synchronously because you flush your whole pipeline and then you have bubbles and stuff. But here we also have a multiprocess architecture. The GPU driver is not in the same process as JavaScript. So for example, in WebGL, if you call GL get error, there needs to be a synchronous IPC from the JavaScript process to the GPU process and back. And so that causes a bubble on the CPU side in the communication between these two processes. So in WebGPU, a major point of the design is that no such bubbles are possible. And so there's the whole error model and stuff all happen asynchronously. So you create a texture and it just looks as if it worked, and maybe the texture is an error, but you don't get to know synchronously. You can only know asynchronously, so that we keep the cross-process communication bubble-free.
Okay. So it's interesting because what you're describing, I haven't worked in the Chrome code base, but looking at various 3D renderers, it's very common to have different backends because you're going to support different graphics APIs, and you have the same exact problem you're describing where that backend is going to be not in a different process, but on a different thread. And so that's a fairly common technique, it seems, to you effectively just create handles and they only represent the real resource at some point later. So there's a lot of like async future promises, things like this that you have to handle.
Yeah, exactly.
So yeah, so Chrome is basically like a game.
A game engine, yeah.
A very fancy one.
Yeah, I mean, let me say it was a stroke of genius by the OpenGL architects to phrase all of the GPU objects as opaque handles. And similarly, Corentin and Kai and many others in designing WebGPU's handle architecture and asynchronous API design. It was another stroke of genius, really taking it much, much farther than OpenGL even did.
I mean, sorry.
Yeah, no, sorry. I was going to say what I like about this is that, I'm not super familiar with JavaScript, but I know that you have primitives like async await, which I assume you make good use of in WebGPU, but it's also like a trend in a lot of modern programming languages. So closer to Android in our world, we have Kotlin with coroutines. And so these asynchronous heavy APIs map really well to this new way of programming that developers are getting used to. So it's nice to see like different sides of the programming world like align on similar concepts. And OpenGL, in that regard, like I think one of the things that made it difficult to use is it was designed for C basically, which made it highly portable, but that also made it extremely awkward to use from Java or Kotlin, or I assume, even in WebGL, like you had to like contour the APIs a little bit, I remember.
Yeah, I remember that dealing with some of the Android wrappers that we have. We basically have thin JNI wrappers over our OpenGL ES. And it's awkward sometimes. There are clearly APIs and approaches to doing GL programming that came from, original stuff on C, like OpenGL, the original desktop OpenGL was like early 90s technology, and then they sort of kept building on it from there. So, clearly we can do things that make it a little more compatible with the way people write apps and code now. On the other hand, it's pretty impressive that it's lasted this long in its various forms, go into GLES and being able to integrate shaders, and like a lot of the new paradigms is just at some point, just like Compose compared to the Vue toolkit, like it's time to do something new because you can only take it so long before you're just making it more and more complicated to build onto the existing structures.
I really like what you said about WebGPU. Like it maps much better to modern programming languages than like OpenGL that was made for C. Like WebGPU is made for JavaScript first, and it's a programming language with async await. It has dictionaries. It has a garbage collector, and that's a huge constraint for the design of WebGPU. And I think that makes it a good fit for other garbage collected asynchronous languages like Kotlin or others, because we had to solve all of that for JavaScript. For example, you don't control the lifetime of most objects because the garbage collector is going to do it for you. But there's a couple objects like textures and buffers that consume so much memory that you want to be able to delete manually, not waiting for the garbage collector to realize that maybe something is using a lot of memory on the GPU, and how does that even work? So you can destroy these explicitly, which means you lose all further access to the texture. You don't have to explicitly wait for operations on the texture to finish, because we take care of that for you for security and convenience. But you can free the memory even though you're in a garbage collected programming language.
So speaking of garbage collectors, maybe this is a good time to say, so what about, how does this thing work on Android? So I know there's some capability to use this stuff on Android, but we've been talking about this JavaScript API, and that makes my brain hurt, right? So how does an Android programmer use a JavaScript API, or how would they approach using this in general?
I actually have a question that I think merges with yours, so we've been talking about WebGPU, and it's in the name, right? It's for the web. And yet, I've heard about WebGPU in many other contexts. Like, for instance, the Rust community seems to have adopted WebGPU massively, and it sounds like all graphics programming in Rust is being done through WebGPU and not not GL Vulcan. So, yeah, how do you do that? Like, can you escape the JavaScript world? Like, how does that work?
So when we designed WebGPU, like, of course, it was meant for JavaScript first, but in the back of our mind, and I think I can speak for myself and also Dimitri Malachau at Mozilla, who influenced a lot of the design and created the WGPU Rust crate. Usage in native of this API has always been top of mind. Both Chrome's Library and Firefox Library are available as just libraries you can use in either Rust or C++. So in native, we're trying to, we say standardize, but agree on a shared header and semantics in C with Mozilla, so that both our implementations can be targeted with the same C code. And then you can choose whichever works best for you, etc. And so the idea is also with this, there will be a bunch of ecosystem, tutorials, documentation, whatever, best practices that show usage of this C API, which becomes the de facto standard for WebGPU in native.
So if I'm an Android app developer and I'm not using the WebView, but I don't want to use Vulcan, I don't want to use OpenGL, I can get the implementation of WebGPU from either Chrome or Mozilla, and then through JNI or just with native code, I can just use it.
Right now through the native code. We're thinking of making GNI bindings, but you need to use native code right now, and the implementation is still being polished for Android, of course.
So let me see if I understand all the wrappers there. So we have a JavaScript engine that's talking to the engine that's sitting inside Chrome that's talking to the GPU. And then on top of JavaScript, we have C bindings that you can call from native code. And then on top of that, presumably an Android developer working in Java or Kotlin would then have wrappers in Java and Kotlin. Ken's shaking his head.
There's a few too many layers in that layer cake.
All right. So how does that actually work?
Thinking about the native Android application, it would just compile in, say, Dawn, the Dawn library, which is Chrome's native implementation of WebGPU. It's just, C++ code. And so that Android native app would talk directly to Dawn, which would talk to Vulcan.
Okay.
Or OpenGL coming soon to a platform near you.
Yeah.
And so that it's a fairly simple and self-contained application stack.
Right. So instead, we can see the JavaScript API that you have in the browser is on top of Dawn. So it would be a peer to, it's a Kotlin API or a Java API through JNI for a Java developer. It's just...
Okay.
So that's exactly right. But Chet, what you described is more akin to what you would do if you were compiling Android app for WebAssembly somehow, and putting it on the web. So you would write an application that uses WebGPU, compile that to WebAssembly. So when you use WebGPU, it talks to JavaScript, and then it talks through the JavaScript WebGPU API, and then you have all the flow in Chrome. So you can stack things as much as you want.
That's the great thing about software. We can always add another layer. But if I were writing a book, at this point, I would have an asterisk. And in the footnote, I would define what WebAssembly is, because that's a new term you just tossed into the conversation. So how does that relate to all this stuff?
WebAssembly is a remarkable new standard which lets you take native applications and run them on the web. It's got a remarkably small set of execution primitives and data types, and a bunch of abstract CPU operations that are specified. They're not just like, okay, we took LVM bitcode and turned it into our spec, which far too many compiler projects have done in our industry, and it always ends in tears. And with this, you can basically take a native application. You need to abstract things like the window management, for example, because that's not going to work transparently on the web. But then you compile it with the mscript and toolchain, which has a lot of emulation libraries built into it. And it allows you to basically take that native app and run it on the web on top of this WebAssembly virtual machine, which is a peer. It's basically integrated into the JavaScript virtual machine.
Yeah, I have experience with that. Our filament 3D renderer, we do have a web target, and the filament itself is a pile of C++ code that talks to Vulcan and OpenGLES and so on. And to compile for the web, all we do is say, hey, you're going to use OpenGLES. You're single-threaded, because that's a whole other discussion. But then, it's pretty amazing. Through mscript, and by just effectively swapping the native compiler, we end up with this WASM file that just runs in the web browser, and we have to do very, very little. In a fairly massive code base, right? Dozens of thousands of code lines. There's only a few cases of pound define, are we the web version? And I'm always amazed that it works this well. And performance good too.
So I'm gonna take a left turn here. I'm always interested in sort of tech history and how things connect. And I guess the first question is, where did WebGPU come from? So we had this WebGL thing. What was the trigger to say, that's enough, on to this new thing?
Well, there were some discussions in Khronos, which is the standards body that hosts OpenGL and WebGL and Vulcan. And there were discussions internally at Google, I think probably with some other companies as well, to try to figure out what should we do for WebGL next.
Well, because I think there's an interesting piece of context here, which is with the birth of Vulcan, OpenGL and OpenGLES have been effectively stable, let's put it this way, or frozen in time since, 2014, 2015? It's been many years. So GL was not evolving anymore. So yeah, that definitely begs the question of what does that mean for WebGL if the rest of GL, the GL family doesn't change?
Right. All of a sudden, the web API would have had to, assume the mantle of carrying forward all these new features, trying to integrate them into the OpenGL state machine, specifying again all these interactions. It would not have been tenable. So many discussions were had among many folks with many differing opinions on what that API shape should be. And not to go into too many details, it was decided that a clean break was needed. And Corentin and I think maybe Kai came up with a proposal called NXT, the Next API.
But before we get there, I assume so. As you said, the standards body said, okay, enough with GL or maintenance mode or whatever. We're on to this next thing, which is Vulcan. So then that begs the question. Okay, well, wasn't somebody thinking, okay, what about Web Vulcan?
Oh, that was considered and proposed.
Okay,
it's not workable.
Right. I mean, it seems incredibly too low level to lend itself to that. Right. But then, how far did that go before people thought, no, actually, we need a higher level thing?
I would say early discussions in Khronos took place over a period of a few months. And when, one party's opinion was, okay, we should do Web Vulcan, I think the majority of the folks in the room said, yeah, we're not going to do that. It was hard enough to specify all of the undefined behaviors in the OpenGLES spec. Mm-hmm. That was necessary to make WebGL a portable specification. There were many, many corner cases, even in that specification, that had to be defined one way or the other. With Vulcan, it's even harder. It's a very chatty API. It's very low level, and you expect to be able to do synchronous memory mapping for most of your application to function.
And there's also the problem of developer ergonomics, right? We talked about WebGPU being designed with JavaScript in mind, and there's a reason why, for instance, on Android, we do not have Java or Kotlin bindings for Vulcan. Part of it is the nature of the Vulcan API means that we would lose what makes Vulcan so good for some developers, that you know, it's so low level that you can do something really efficient. But then if we have to make so many GenI calls and we have to slap a garbage collector on top, then you start losing the benefits of having that extremely verbose API in the first place. So to us, it doesn't really make sense to like put you there. And also, I think it doesn't meet the expectations of your traditional JavaScript, Java, Kotlin developers in terms of complexity and ergonomics in general.
So, like, while now, I think everybody agrees that this is like Vulcan is really hard to use and would be a bad fit for a language like JavaScript or Kotlin. At the time, we had less perspective on how much effort it took to use Vulcan. I mean, we kind of knew about it, but it was not that clear. And so most of the discussion at the time were more about feasibility more than ergonomics. So we published an NXT design doc, which was our proposal to the WebGPU group. And there's a whole section which is why not Web Vulcan? And it goes into what Ken said, where all the undefined behavior are almost unworkable. The API is not easy to remote across the GPU process, etc.
So it's interesting you say that, because to go back to a point I made earlier, with WebGPU reminding me a lot of various rendering engines or game engines, the first time I saw the WebGPU API, and even more so Dawn itself, right, the library underneath it in Chrome, the level of abstraction it provides is strikingly similar to the kind of abstractions that rendering engines and game engines build, for a couple of reasons. One is to smooth over the difference between the various graphics APIs that you have in your backends. And another one is just to also hide the complexity of what you have to do, especially with the more modern APIs. So yeah, I still think it's very interesting that, you know, we have those super powerful low-level APIs, but really for most app developers, that is not what you need nor what you want. And they're very easy to misuse. And I think both you, Ken, and Corentin mentioned that, you know, it's easy to do something wrong with Vulcan. I want to stress out how wrong it can be. So probably not on Android, but on desktop, I've definitely locked up my entire machine where you have to do a hard reboot because, you know, Vulcan gives you that power.
There was, I remember a trend from the 90s when you would have a really low level thing like D3D, and then people would want to create a scene graph that sat on top of it. And I don't remember any successful scene graphs, because if you go too far, then all of a sudden it starts getting very domain specific, or you have to be domain specific for it to make sense. Like it's easy to build, well, it's not easy, but it is doable, obviously, to build this low level thing. Even the lower level thing like Vulcan, it's harder to build a scene graph API that everybody would want to use, because then it has, you know, too much overhead for their use case or not enough features or whatever. So you end up having like game engines that do specific things, but you didn't end up having a good higher level concept for a lot of the low level things. And I wonder in the Vulcan space if that was the original thought, was like, yeah, everything's low level, but then we'll build a scene graph, and then you can put, you know, the APIs on top of it that make sense and are easier to use. And if that just like didn't come to pass, or, you know, ran into the normal problem with scene graphs, I was sort of curious how that developed.
My understanding, and like keep in mind, I wasn't working on Vulcan stuff back then, but like it's just from what I understood. What you described is exactly what happened, where they were like, okay, we need to provide low-level access, almost console-like access to GPUs for game developers to do amazing things. And eventually, there's going to be helper libraries for things. There's one such good success story, which is the Vulcan memory allocator. So that's a library made by AMD, I think, that
it's AMD
papers over memory allocation for Vulcan, because of course you have to write your own GPU memory allocator. And nobody wants to do that. But I think that's about the only broadly used helper library for Vulcan. And there's never been a more like scene graphy or easier to use abstraction, except if you take like Unity or Unreal or such engines that just port to Vulcan.
I would say there's another set of libraries/tools, shaders, right? So we haven't talked about WebGPU shaders, but in Vulcan, shaders are in what's called SPIR-V, which is effectively a binary representation. So it's not like if you come from GL where you write your shader as text, in Vulcan, that's not what you feed the Vulcan API. So you have to compile at some point your shaders into this SPIR-V thing. So what happens, especially and I assume Don has to do something like this, where if you have to support multiple backend, you need to write your shaders in a more general language, and then you transpile it or compile it to SPIR-V at some point. And so there's a few, Microsoft has a compiler, there's the GL Slang open source library, and those are widely used, right, with Vulcan.
Wait, isn't a JavaScript API like really compatible with shaders because they come from this weird world where it's just strings that you eval at runtime, right? So doesn't this just work? We'll just pass it a string and then the shader will be, just evaluated.
Okay, but then you need to define what's in the string, and that's the difficult part. So I think that touches on a good point, which is WebGL had its own shading language, which was basically GLSL, the same one as OpenGLES's shading language. But WebGPU, there has been a controversial decision, which is that WebGPU created a new shading language that's not any of the ones that is not close to any of the ones that was used in industry previously. And that was a very like multi-year decision to take in the WebGPU group. Like to really, it was amazing. The hardest thing we did. And it's still controversial to this day, but I think what we believed back then, and it seems to be happening, is that the shading language ecosystem just papers over that. Everybody uses, all the engines and all portable applications on GPUs use giant stacks of shader compilation things. And often in the middle sits SPIR-V. And for example, we're building a SPIR-V to WebGPU shading language converter. And so hopefully that papers over differences for devs.
So it's interesting because I've been following that controversy, but when you take a step back, I think, providing SPIR-V as the shading language for the web doesn't really make sense because you start introducing toolchains in a world where like the power of the web, that's always been amazing with WebGL, for instance, that you don't need a toolchain, right? Like you just write your JavaScript, it just works. All you need is the browser. And then when it comes to the shading language, like, yeah, you could adopt one of the existing ones, but then I think we go back to what I've seen before, where when you use a shading language that was not meant for the graphics API you're using, you regularly run into like really awkward situations where like the language doesn't really map to some of the concept, or you're missing features, or they have to be bolted on. So I don't know, to me it makes a lot of sense that WebGPU has its own shading language that can evolve in parallel with WebGPU itself.
I'd like to give a shout out to some of our team members. Dan Sinclair in particular, and Corentin collaborated on the initial WebGPU shading language proposal, which I personally added a lot of noise to the conversation back in the day. Thinking that SPIR-V was the path forward because it was specified, firm, well-defined specification that ran on a host of hardware. But Dan and Corentin, and also, shout out to David Netto and Ben Clayton and James Price and Antonio Majorano, all on the Tints team, helped define exactly how you would take SPIR-V primitives and up-level them to a text-based shading language. That was the key, because the only portable definition of the GPU functionality in shading languages is SPIR-V. HLSL runs on, not all the hardware that's out there. It's spec for...
So HLSL is the shading language for DirectX.
Yeah, that's right.
But I think it's also what's used on console. It's very popular in game engines as the universal language.
Yeah, that is true. That is true. And, other shading languages that exist out there are Metal shading language for Apple hardware, and only Apple hardware. I want to underscore that point. And also, of course, GLSL, the OpenGL shading language. And none of these were really appropriate as a choice for targeting WebGPU.
You mentioned Tint. What is Tint?
Tint is Chrome's implementation of the WebGPU shading language compiler. And it's now actually part of the Dawn repository. So it's a separate component, and it's very, very useful. It can take in WebGPU shading language and translate it to native platforms. It has a SpearV front end and actually a SpearV backend as well. So it can do a lot of very interesting transformations between various shading languages. And it can also be compiled as a user level library.
Yeah, so for our listeners, you're discovering an aspect of graphics programming. When people think of graphics programming, they imagine like fancy shaders and beautiful visual effects. But they don't realize that graphics programmers do two things. They move buffers around and they transpile shaders. That's all they do. One of those two things all the time.
And so in terms of shader transpilation, previously there was the only shader transpilation toolbox there was were things targeting SpearV and then a project called SpearV Cross that translated SpearV to GLSL, MSL, HLSL, all the shading languages. But with WebGPU, there's at least two other shading language toolboxes that are appearing. There's Tint, which we just touched upon, that can take in SpearV and WebGPU shading language and output approximately any shading language you want. But there's also Firefox's equivalent that's used in their library called WGPU in Rust. And they can do approximately the same thing. So it's just better. There's a larger ecosystem for shader toolbox now.
So to go back to what Chet was saying earlier about the fact that programming is layers everywhere. So I'll use the example of Filament again, where we write all of our shaders in GLSL, we compile them to SpearV, and then we transpile that back to GLSL for desktop, GLSL for mobile, or for web, or Metal SL, or we leave it in SpearV if we want to target Vulcan, and we'd like to add a WebGPU backend, in which case we would add Tint to go from GLSL to SpearV back to WebGPU SL shading language, so that then Chrome or whatever's running WebGPU would bring it back to SpearV. So again, proving my point that all graphics programmers do is transpile shaders.
So I'm curious, though, the fact that you can go back and forth between all these myriad of infinite possibilities in shaders means there must be like a huge proportion of functionality and concepts that are shared between all of them, right? Like WebGPU has a new shading language. It is not GLSL or HLSL, but it must be fairly close in functionality. Otherwise, it'd be kind of hard to go to all of these other things, right?
Yes, there is a portable subset of all of these shading languages, and I think that's the thing to underscore here. Some of the shading languages have constructs that aren't compatible with others. Some accept full C++, and that is supported in some of the other platforms' tool chains, but not everywhere, and so that had to be disallowed as a concept in WebGPU. We're not just going to have C++ as the shading language. So SpearV really, I think, represents the portable subset of this functionality, and that's what is ensconced in the WebGPU shading language.
I would just add what helps in the end is that we're targeting the GPU, which is not a general processing unit. So it's about doing math, a lot of math, and all those languages fundamentally are imperative languages. You have structs, sometimes C++, but they're fundamentally very much the same. So the core, most of what you do in your shaders can be transpiled between those languages because it's in the end very simple. And then at the edges, yes, there are issues, and all that transpilation I was talking about, that's why you end up with like those piles of libraries that Corentin mentions, because there's a lot of edge cases to take care of. But yeah, the vast majority of the code is fairly easy to transpile.
So
Corentin had his hand up.
No, it's okay.
And then it went down again. So I was going to jump back on my history train again and point out that when you brought up garbage collection, I realized, okay, so Romain and I in the room have a long history connection with Ken, but then I realized, even more than that. So Ken, you come at an interesting cross-section where the original context I knew you in at Sun Microsystems was you were a runtime programmer. You worked on garbage collectors and runtimes for the Java programming language. And then you took on this Joggle stuff because your real passion, even though you were a runtime programmer for many years, your real passion was graphics. So you started doing Java OpenGL bindings. And then I guess that eventually led to, future lives working on WebGL. But at the same time, we gave a talk in 2005, I think, at Java 1 called Filthy Rich Clients, which led to other interesting things. So I just wanted to point that out because nobody cares but me, but I wanted to get it.
I'm going to add one of my earliest memories of Ken. I was an intern at Sun Microsystems, messing around with the Swing UI toolkit and OpenGL. And then I was talking to Ken, he was helping me through that. And one day he comes back in my office, very excited, tell me that he just made arrays faster in the VM, just the thing that someone does on a day-to-day basis.
It was a lot of fun. I remember the time when I was working on the Java hotspot runtime and thinking to myself, actually, the biggest problem is not Java execution performance right now. It's the ability to deploy rich Java-based applets in the browser. And so I transferred teams to go work on the Java deployment team and try to shore up the Java applet runtime.
Yes, I remember that. I was still there at that time. Yeah.
And we successfully moved it out of process, which was an architectural transformation that was necessary to make it as robust as, at the time, Java Web Start. And it worked. We actually shipped that in Java SE 1.6. something after a long development incubation time. Anyway, that gave me personally the experience to be able to walk into Chrome and say, oh, inter-process communication primitives. We had to do that for the Java applet runtime at the end, so understood that.
If you think about it in terms of timing of the other things that were happening in parallel, you can sort of see why some of the stuff didn't pan out in the long run, because I think you probably moved over sometime around 2007. The iPhone launched in 2007 and famously said no other runtimes on this platform, which included eventually Flash, which was trying to get there, and also HTML5, which was coming online at the time. And so Java at the time and Java applets provided a way to have rich content in the web, and eventually that turned out to not be the solution that people wanted. So all of these things were happening in parallel, and they shall not all win that game.
Yeah, I mean, that's what's so exciting to me about WebGL and now WebGPU is the fact that built into your browser as a standard, so all the browsers, either now or eventually, you have access to not only like powerful graphics capabilities, but Corentin mentioned and Ken, you mentioned compute shaders, and for the listeners who don't know what compute shaders are, it's basically the realization that GPUs now are just massive calculators that can do a lot of math. And compute shaders are just a way to tap into that capability without having to output pixels in the end, which allows us to do things like AI, ML are one thing, but it's just like physics simulations, and they're heavily used in games and other applications today. So there's a lot of very interesting things that can be done on the web, and it doesn't have to be visual because now you have this high-performance computing API at your disposal.
So when we're talking about the web, you're writing it assuming that people can run this thing everywhere. And as you said, Ken, you need the engine, and we have the engine inside of Chrome and apparently Firefox. So what is the adoption of this thing across all the myriad of browsers that people happen to be running?
And hardware, like what are the hardware requirements?
So I'll start with hardware requirements. We try to design WebGPU so it runs on the vast majority of hardware where people have browsers today. So I think we want to run, on all devices that have all the Windows 10 machines, almost all the Macs, all the Chromebooks eventually. On Android, we want to run everywhere that has Vulcan, of course, but also OpenGL ES 3.1 eventually. Of course, because we need compute shaders and they're not in OpenGL ES 3, we're not going to emulate them. That would kind of defeat the purpose. So the goal is that WebGPU's reach is very broad on the core specification, and then there's optional features that are available depending on the device.
I would have to check the exact numbers, but to give our listeners an idea, I think OpenGL ES 3.1 on Android is probably around the 95% of the device population. It's basically everything.
Yeah, everything shipping with a GPU today should be able to run WebGPU, basically. For the browsers, I mean, Chrome shipped WebGPU, and other Chromium-based browsers are doing the same. Firefox, you can try WebGPU in Firefox nightly. I mean, they're just trying to complete the implementation so they can ship WebGPU as well. They give some timelines, but my bet is end of year, beginning of next, not earlier. And WebKit, which is used by Safari, there's no official comments, but looking at the GitHub repo, there's active implementation ongoing. So fingers crossed that it happens at some point. So it should be in basically all browsers soon-ish.
We'll get some links from you for places that people can find, tools that they need to actually play around with this stuff. So we'll put those in the podcast notes.
Yeah, and so actually, if I want to learn about WebGPU, learn how to use it, like, do we have a dedicated website? Are there resources that people should look for?
We have a bunch of resources. I think the best one to learn WebGPU would be the code lab we made for Google I/O. It's in JavaScript, and it takes you through the implementation of the Conway's Game of Life in WebGPU. And it's, even if you don't know GPU, it should be fairly approachable. For WebGPU use in native, we don't have dedicated tutorials for how to use the API in C or C++, but everything you see about JavaScript kind of translate one-to-one to C, C++. We do have a couple blog posts on how to compile applications with WebGPU in C, C++. We want to have a dedicated website with links to everything at some point, but it's not there yet.
Soon-ish, I'm thinking.
I would also highlight our colleague Greg Tavares' WebGPU Fundamentals article series. He's got a lot of stuff. He wrote WebGL fundamentals and now has been fleshing out the WebGPU side of things. That's a very good resource for learning the API.
Yeah, and it's one of the things that excites me about WebGPU is knowing that it's going to be available on the web and it's a standard across all the browsers. There's going to be naturally a lot of material, like lots of documentation, tools, examples. And then if you want to use WebGPU from Rust or like using Dawn or the Firefox implementation, like Corentin said, like you can basically tap into all that documentation and all those assets to help you. So I'm excited. It sounds like it's going to be really good for the graphics community at large.
Yeah, I'm positive that it is. Also, our colleague Brandon Jones is already a WebGP Best Practices series. Maybe unofficial, it's on his blog, but he's got some great examples there, like how to design a GLTF loader and renderer. And he went through multiple iterations showing you, all right, here's what you would do naively, and this isn't fast.
I have seen those articles, yes.
Yeah. Then you refactor it until you're at what you can do with the native APIs. It's really fantastic.
I'm personally a fan of the code lab you mentioned just because I can remember writing basic code on an Apple II Plus in the early 80s to write the Game of Life. So it's nice that we can support that on WebGPU. So we have all the power of the universe at our disposal, and we're going to write the Game of Life because that's what we do.
No, it's really exciting to see WebGPU take off because we shipped it only a couple months ago, and there's so many there's a lot of force behind it and a lot of push to use WebGPU in a bunch of places. I think what's most exciting to me right now is Chrome is re-architecting how it's doing GPU rendering, 2D GPU rendering. And instead of targeting each API individually, Skia, the library that powers 2D rendering in Chrome, is looking to just target Dawn. So in Chrome, all 2D rendering is going to go through WebGPU essentially.
It goes back to what I was saying, right? Everybody writes all those backends. So if you've done that already, why not reuse that?
Yeah, there's always a question of control, right? Like if you use a off-the-shelf WebGPU implementation, then you might not be able to use that tiny toggle somewhere in the GPU API, but you gain a lot from just saving work.
So anything coming up that you want to mention, or do we not talk about future developments?
No, we're very happy to share things we're working on. So a big one is the addition, we're trying to push the addition of a compatibility mode in the WebGPU specification so that WebGPU can run on D3D11 and OpenGL ES 3.1. So that's to give the reach of devices I was talking about earlier. And the idea is like most WebGPU code needs no modifications to work. And the other exciting thing is that we're trying to look at what it takes to make a better version of like to make GNI bindings for Dawn, etc., and like what it would take to make things maybe idiomatic in that world, which I don't know anything about. And that's kind of exciting. It's just you would have WebGPU in all the ecosystems. which is crazy good.
Nice. So we're probably getting to the end now. Did we forget to ask anything that you wanted to talk about? We asked all the questions.
Nothing comes to mind specifically.
All right. Then I guess that's it. Thanks.
All right.
Thanks.
Thank you all.
Thanks for having us.